Hey guys, so this is my machine learning project. Basically, I'm trying to predict if I like a song on Spotify or not. So it's a classification problem, and I'm going to be using the Spotify API to get this data. So the inspiration behind this project was that personalization. It's one of the biggest things in consumer products. Basically, personalization is to observe user behavior, check their taste, their preferences, and kind of personalize the user experience for them so they stick around for longer and stay loyal to the product. And this is used by some of the biggest consumer products out there like Facebook, Twitter, Instagram, Apple News, and streaming services like Netflix and of course Spotify. And the systems that these companies use are obviously way more complex with a mixture of different kind of machine learning models, but I'm trying to mimic one aspect of Spotify, which is the Discover Weekly playlist. It's a playlist of music that I might like, which is you know based on my previous listening history. So let's jump into the data and kind of look at how that's structured. So Spotify, each song in Spotify has something called audio features that makes up the DNA of a song. So let me go into the documentation to kind of show you what I mean by that. So yeah, each song has an ID, it has a name, and then it has all these features which each mean a different thing. Acousticness, uh, to tell you if a track is acoustic or not. Danceability, energy, if it's high energy or low energy. Instrumentalness, liveness, loudness, speechiness, tempo, and valence. For example, valence is a measure that tells you if a song is sad or happy. So if it's closer to zero, it might be a ballad. If it's closer to one, it might be a really upbeat pop track. And yeah, so I think that these are like some pretty cool numerical features that could be used to predict if I like or dislike a song. And the way I'm going to be getting this data is to connect to the Spotify API, and I've created two playlists on my Spotify account, one of songs I like and one of songs that I don't like. And let's just jump into the code to see how I extracted that data from Spotify. So yeah, the first thing is, you need a client ID and client secret. You're going to be using this in the post request to get something known as an access token. This access token will be used in future GET requests, depending on the API endpoint, to get data from Spotify. And then I had to create a bunch of functions to get data from Spotify, and there were a few issues here, namely that Spotify has rate limits. Each GET request returns only 100 objects at a time. So I had to like repeat this a number of times by setting an offset value. I had to create a number of different API endpoints, write a bunch of for loops, put the system to sleep for some time, and then combine all the data that I could get. The first pass was just names, IDs, popularity, and duration. And then I had to create another function to take, which basically takes a data frame of tracks that I got from the previous thing and extracts all the audio features that I just spoke about. And same issue here, rate limits, bunch of for loops to like go into the JSON object and pass everything out and put the whole thing together as a data frame. And finally, a last function to put those two functions together. Basically, take a playlist ID as a parameter and the maximum number of songs that I want to extract from that playlist. And then yeah, I created two data frames of songs that I don't like and songs that I do like. I've added a target variable to both. Zero means I don't like a song. One means that I do like a song, and then put them together. So let's just take a look at how that data looks. I've run this code before because it takes a really long time. So here you can see most of them are numerical features, and you have the names and IDs. And if you look at the structure of it, it has 3,000 observations of 17 variables. As I said, most of them are numerical. Right, so that's how I got the data. The next part is data preparation. So that's like checking for missing data, exploratory plots, correlation, normalization, and PCA. So there was no missing data, so there was nothing to impute. And then I plotted various. I plotted two things. One was a distribution curve or histogram, and the second was a box plot to check for outliers, and also check for the skewness in the data. And let's look at a few of those plots and see how that looks. So I kind of sorted them based on songs I like and don't like, and give them different colors to see, where there's an overlap and where there's like a clear distinction of songs I like and don't like, and how each feature impacts that. And this are, for example, tempo looks, and then you can look at valence. So there's some overlap at the same time. It's clearly distinguished as well. Uh, right, that's one aspect. And then checking for outliers through box plots, there were not many outliers. Most of them did have. And when they did have outliers, there were just like a couple of them, so I just ignored them and didn't really try to remove them. And finally, I calculated the correlation of all these numerical features with the Pearson method, and then I plotted that, and this was the result of that. So yeah, this shows you the correlation each feature has with each other, as well as the target variable, which is in the last column. So each feature does have some kind of a correlation on the target variable. Blue stands for positive, red stands for negative, and the size of the pie chart tells you how the intensity of correlation, basically. So I'm going to be using all the features for creating the models. And then finally, I principal component analysis. I use the function called prcomp. Before that, I did normalization. Sorry, so I use the scale function, which basically does a z-score transform, and then the PCA on the numerical features using the prcomp function, and kind of plotted that too. Not sure what exactly this does, but yeah, it's just a plot of the PCA data, and I extracted the useful parts, added back the target variable, and created the final data frame, which I'm going to be used for creating my training and testing data sets. So yeah, jumping into the modeling, I use three classification algorithms: KNN, support vector machine, and decision trees, all from the Caret package. And each of these were put through holdout data with holdout method, data with cross-validated data with K4, and then finally with tuning. And the last thing was a stacked ensemble method. So I split the data 70-30 and using the create data partition from the Caret package. And so I'm just going to explain one of the models in depth, because all of them just follow the same pattern after that. So the main function from the Caret package that you'll be using to create a model is the train function, which takes the target variable and all the feature variables that you want to use to predict it, the training data that you're going to provide, and the method that you want to use. So in this case, it's KNN. In the next case, it's SVM, and finally, it's decision trees, right? So this is basically how each model is built. And then when it comes to predictions, I've entered type as a probability, because I want to calculate accuracy based on ROC and area under the curve, and that's possible only when you have the response as a probability. At the same time, I also converted it to 1 or 0, yes or like, so I could also plot a confusion matrix. And so yeah, and then using a library called RORC, I think, I got the ROC values and the AUC values, and I put them into different variables. So this is done for KNN, done for support vector machines, done for decision trees, and after all of that, a summary of all three was put into a data frame. And the highest value of AOC was for SVM at 0.99115. So without any cross validation or whatever, just using a 30-70 split, SVM won out. So the next thing was K4 cross validation method. So yeah, so if you want to do cross validation and with K4s or when it is repeated cross validation, you need to include a few parameters in the train control aspect of the train function. So here you see the method is CV. You could also give repeated CV, and the number of folds you want is equal to 5, and number of times you want to repeat you could add as another parameter. So I'm just going to stick to 5-fold cross validation, and so you can see that that's added to the train function over here. Again, same thing for support vector machines, and the same thing for decision trees. And when I looked at the AOC values for all of those, the one with the highest AOC value again was support vector machines. It did slightly better than without cross validation. I think 0.0000.56, some very negligible, but still an increase in accuracy. And the last aspect were tuned models. So tuning of each model depends on the kind of algorithm you're using. So for KNN, you vary the K value, to see if you're going to get a better accuracy. For SVM, you vary the sigma value and the C value. The C value is basically a parameter that tells the SVM how much to avoid misclassification. And finally, decision trees have something called CP values, which basically is the optimal pruning of decision trees. Pruning is basically cutting down on trees and shaping them to look pretty in the real world. So that's like a metaphor for the model as well. So yeah, so and how you tune in the carrot package is there's a parameter called tune grid, and you feed it a bunch of values based on the algorithm. For example, KNN, it's the K value, and these values are kind of selected based on the optimal value on the previous thing. So the previous one had 5 or whatever. So take values in and around that to see if you get a better accuracy. And again, for SVM, you have sigma values and C values. So based on the previous C and sigma values, you take a few values in and around to see if you can get a better accuracy, and you feed that into the train function. And finally, for R part, you feed it a data frame of CP values in and around the previous value that you got. So after tuning all the models, of course, obviously, like I think SVM had the best AOC again, with 0.9913667, again a slight increase from cross validation aspect of it. And yeah, so that was individual models. Then I tried a stacked ensemble model from the Carrot ensemble package. And the algorithms that I stacked were RPart, KNN, and SVM radial. And I got an accuracy of 95.15. I couldn't figure out how to get the AOC and ROC for this model. But yeah, in conclusion, I think the best model was the support vector machine with a bit of tuning of sigma values and C. So yeah, that was fun. Thanks for watching, and look forward to your comments.